So I want to pick up where we left off last week with exponential functions. And specifically, I think we're doing pretty well with initial values, right? Like we understand with that van problem from last week, the purchase price, $40,000, is the initial value. We're doing great with that. The question that I want to get into today is, what about growth factors, though? And unfortunately, Google has no good answers here. But I want to zoom in on growth factors because I think this is the complicated idea, the most complicated idea in this unit. So let's get into it. Now, here what we have is an exponential function, 3 to the x, or 1 times 3 to the x, if you like to see that initial value. And I just want to show you something about this growth factor. Now, the growth factor is 3, obviously, right? You can see it here in the function. You can see 3, times what gets us up to 9. That's got to be 3, right? This is no problem. We can say the same thing, right, from the initial value up to 3, right? 1 times what makes 3. That growth factor is 3. What I want to show you that's maybe less obvious is that this growth factor stays 3 no matter what pair of points we pick. So we saw how it worked from x equals 0 to x equals 1. We saw how it worked from x equals 1 to x equals 2. But check out, if we slide this around, right, our y values are changing plenty, but our growth factor is always 3. Right? And that may be a little bit less obvious here, but if we wanted to calculate this growth factor, we could use that technique we've been using for years where we take, or not years, but a year, a later term, 18.18, divided by an earlier term, 6.06. And sure enough, if we do that in Desmos, hey Desmos, what is 18.08 divided by 6.06? Maybe you already know it's 18.18, excuse me. The growth factor is 3. Right? So I think this is a pretty cool idea that growth factor is always, always, always going to be 3, no matter which pair of points we're using on the entire function. That's actually an idea from Algebra 1. So here's where we're going to take this that's even more advanced. What if the distance between our points isn't 1? Right? Instead of going from x equals 1 to x equals 2, what if we want a distance of 2? Now, this shouldn't be too surprising, but this is now like 2 growth factors, right? From x equals 1 to x equals 2, that's like times 3. And then from x equals 2 up to, I didn't get quite high enough, all the way up to x equals 3, that's another times 3. So the overall growth factor is times 9. In other words, when that distance is 2, our growth factor is 3 squared. And again, this works no matter which pair of points we pick, right? If we go from 0, if we go from 0 to 2, right, we grow from 1 to 9. That's a growth factor of 9. If we even zoom out and go from like 2 to 4, right, that's a growth factor of from 9 all the way up to 81, right? And this works even at fractions. If we go from 1.5 to 3.5, we can see how the growth factor is still times 9. Here's where things get really trippy, right? And just for the record, if we had a distance of 3, my guess is you're not surprised that the growth factor is times 3 times 3 times 3, right? Or 3 cubed. If we had a distance of 4, the growth factor would be 3 to the 4th power, and this is now getting very, very large indeed. But here, right, this is a growth factor of 81, or in other words, 3 to the 4th power. Okay, now here's where things really get a little bit mind-blowing, is in the Algebra 2 context we're going to be working with. We're interested a lot of the time in what happens with fractional growth intervals. In other words, from x equals 1 to x equals 1.5. What happens then? What we said last week is the growth factor here is 3 to the 1/2 power, right? So that if we do times 3 to the 1/2, and then again times 3 to the 1/2, the overall growth is times 3, right? From 1 to 2 would be times 3. So from 1 to 1.5 would be times 3 to the 1/2 power, or in other words, times the square root of 3. And we can check this just to make sure Desmos isn't messing with us. Hey, Desmos, what is 3 to the 1/2 power? Hey, it's 1.732050, all that stuff. In other words, the square root of 3 is that number. And so this, just like everything else we've seen, no matter which kind of pair of x values you're picking, the growth factor will always be root 3, 3 to the 1/2 power. That's true from 0.1 to 0.6. That's true from negative 0.2 to 0.3. That's true from 1 to 1.5, or from 1.5 to 2. Right? So this idea that the growth factor along an exponential function stays constant works even when the distance we're covering is just 1/2. Right? Maybe you can guess here, what if the distance we covered was like 1/4? Right? Maybe this number doesn't seem to mean anything at first, but hey, I think it means 3 to the 1/4 power in order. In other words, what is the 4th root of 3? 1.31. Right? And this works from 1 to 1.25, or from 1.5 to 1 2/4. This is 1.75. It's just not quite showing. Right? Or from 1 3/4 up to 2. So again, this growth factor stays constant as long as the distance between your x values is staying the same. Your growth factor is going to stay the same. Right? So no matter where on our function we are, if our distance between our x values is 1/4, our growth factor is going to be 3 to the 1/4 power. If our distance is 1/2, our growth factor is going to be 3 to the 1/2. No matter where on our function we are, we'll see that same growth factor, root 3. Okay? So what can we use this for? Well, this turns out to be useful for solving all sorts of problems. Let me show you an abstract one. Don't worry too much about this math, though, of course, if you want to look into it, feel free to poke around. But let's say that we had some x value here out of 1/2, and we know that it grows, a change in 1, right, from 1/2 to 1.5, and we want to know what the heck would this y value be. Well, I don't know how to calculate it directly. It looks to be about 6 something, 5 point something, but if I want to find this exactly, I can use the property that we just came up with. Well, hey, the difference here is a change in 1, so the growth factor is going to be times 3 to the 1st, or in other words, times 3. In other words, this question mark is just going to be 1.72 times 3, which we could do in a calculator. That is, hey Desmos, what is 1.72 times 3? Right? This is 5.16, which, looks about right. This is 5.16, right? This is a little bit above 5 on our y-axis. Let's take an even harder problem. Let's imagine that we start at x equals 1.5, and now we only change 1/2, right? What on earth would this y value? Well, let's actually make this even. Yeah, actually, I like this problem. What on earth would this y value be? Well, I know that, we're starting at 5.2, and I know that this growth factor is over a change of 1/2. So this growth factor is going to be times 3 to the 1/2 power. So to find this value, all we need to do is say this is going to be, 5.2 times 3 to the 1/2 power, or 5.2 times root 3. We can use Desmos to do that calculation. 5.2 times root 3. And this is 9.00. And in fact, if we had if we had a slightly more precise answer here, let's round it a little bit less. Let's go up to 3 decimal places. Oh wait, let's go up to 5.19615. Right, we're seeing basically the number that we're talking about here. Sorry to fiddle. Let's go up to an 8th decimal place. 1524. Right, we're basically talking about the number 9, which looks right from our graph. Right, this question mark has a y value of 9. So you can use this idea about the growth factor staying constant to do all sorts of, to kind of find all sorts of missing information. If you want to, we know where we are now and we want to know how far you're going to be half a decade into the future, right? That's when we might need these 1/2s. So we've seen how those halves can be useful. I realize this is a bit mind-bendy, but the key idea here is that the growth factor stays constant no matter where you are on your curve. And that property is true even if the distance between your x values is a 1/2 or a 1/4 or a 1/3 or 2 or 3, right? That growth factor is going to stay the same no matter where you are on your function. Thanks for this slightly longer video. This is kind of a mind-bendy idea, but good luck with it. I think you're going to get the hang of it.